I am Đặng Văn Hưng, and I have the honor to chair this session for the invited talk from Professor Tobias Nipkow from Technical University of Munich. He is going to talk about verified textbook algorithms. And before his talk, I'd like to give you a short biography of the speaker. That Professor Nipkow works in the area of logic in computer science, and he focuses on interactive and automatic improving programming language, semantics, and type system and functional programming. Dijkstra is developing the interactive group assistance Eberl. Professor Nipkow received his diploma in informatics from the Technical University of Darmstadt in 1982, and his PhD from University of Manchester in 1987. Having had research position at MIT from 1987 to 1989, and Cambridge University in 1989. From 1989 to 1992, he was appointed professor for the theory of programming at the Technical University of Munich in 1992, and since 2011, he has had the chair of logic and verification at the Technical University of Munich. And may I invite Professor Tobias Nipkow to give the lecture to us now.
Thank you very much for the kind introduction, and thank you for all the organizers for inviting me to your conference. It's been a great pleasure for me to prepare this talk for you. Of course, I would have liked even more to present it in person in Vietnam, but I'm trying to do my best online. What is this all about? It's a project that's quite close to my heart for the last couple of years, algorithm verification, and in particular algorithms from the algorithms literature. One project I've been following is actually verifying algorithms from a particular textbook. So this talk is about a specific textbook, namely the Cormen, Lysensen, and Rivest, and that's what we're going to focus on. And the question was, how far have we got in theorem proving? How much of this literature can we actually formalize and verify? And the talk will focus almost exclusively on the verification using interactive theorem provers. And the reason is that most of the material in the textbook, CLRS, Cormen, Lysensen, Rivest, and Stein, is too complicated for ATPs. But there are some exceptions. I will talk about that later. And the talk will also include complexity analysis of algorithms, not just functional correctness, but not so much. I mean, we haven't got that far. We have many algorithms where we have verified functional correctness, but not the complexity analysis. Why is the survey biased? Well, of course, it's biased partly by my own lookout on the field. And you can also see, if you look at the citations in the paper, then 50% of the citations are to the Eberl theorem prover, and then followed by Koch, Y3, and then a number of further theorem provers, the ACL2 system, Hall, and a number of others. But this is not pure malice on my part, but we did actually consult all the major players for input. So we wrote a first version of the survey, and then we sent it around and asked for specific input. And the figures remained as they are, or rather of course, initially it was much more Eberl-centric. Now, I think we did our best to make it fairly even. But another reason why it's a bit Eberl-centric is that we have many references in the paper to work that was published in the Archive of Formal Proof, and not in conference proceedings. What is the archive of formal proofs? It's an online archive of Eberl proofs that users contribute to, and we have a large collection of contributed articles, verification efforts of some size, and 80 of those articles are on algorithms. So you can see we have a large archive where people submit their work and it doesn't get lost, and a number of the citations in the paper are to that archive. So that explains partly why the Eberl is represented quite highly. But as I said, we've been doing our best to really do a most complete survey, but it's a vast field and the presentation is certainly selective, not necessarily Eberl-centric, but selective on what I think is interesting. And the survey paper, we are trying to be inclusive. That is, we try to really include as much of the known verifications that we could. Okay, so what will I talk about? I will first tell you a little bit about the frameworks that have been used in these verifications, and then about the mathematical foundations that concerns mostly the algorithm analysis, the running time analysis, and the much of the paper will then talk about the algorithm themselves, and finally some conclusions. So let's start out with the provers and frameworks. And the first question is, how do you actually formalize an algorithm in a theorem prover in order to verify it? And there's the most immediate method is directly in logic. That is, the theorem prover has a logic and you use that logic to formulate the program. And why that works is that many of the theorem provers contain a functional programming language as a sub-language of the logic, and then you can actually use the logic, or rather that sub-language, to formulate your algorithms. So that's very appealing, and that's also the most popular approach in this survey. For different kind of applications, it may not be so popular, but here it certainly is. And the pros and cons, the big advantage is that it's most effective for proofs. All the automation and tools for the logic are available in your proofs. There is no indirection. You're really directly on the metal, so to speak. The disadvantage is that the only thing you have is functional programs. Logic is by its nature a functional thing, and so therefore your expressiveness is restricted to a particular style of programming. The alternative is you embed some programming language of your choice in the logic of the theorem prover, meaning you really define the syntax and the semantics of some programming language L in the program, in the host logic of the theorem prover. And then you derive verification rules for L, for example, Hoare logic, from the language semantics. And then you use those rules. Now, here the pros and cons are you have much more expressiveness, so you can, for example, define a programming language with arrays and references, which are not part of your standard functional. But the cons is you need special support to ease the pain, because now you have this extra level of syntax and semantics that you have to go through in order to verify the program. So you typically need something like a verification condition generator with all the complications that means. So it's a bit of a trade-off what you want, whether you want immediate access to all the proof methods or whether you want more expressiveness. And there are also combinations of those approaches anything between the pure logic and the embedded programming language. Now, what kind of verification frameworks are there? Again, there are a lot, and I will just talk about two of them that are representative for a whole class of approaches. So two sample frameworks for functional programming plus imperative effects. So here the core is really a functional programming language, but it's expressive enough that you can also talk about imperative effects. And one example of this kind of framework is something called imperative HOL, imperative higher order logic. That's realized in Eberl, and it really has the functional programming language of HOL plus monadic effects and plus imperative effects expressed in a monadic style. So, for example, you can write things like this, even if you haven't seen monads before, you can see there's something that looks like an assignment, and there's something that looks like a return statement. And indeed, this style of defining your code is really purely functional, but it can it allows you to generate code in an imperative language. So in some sense, you get the best of both worlds. Y3 is kind of related, but then again very different. Y3 is a system that doesn't have a theorem prover itself, but it's a programming language, an ML-like functional language with effects, and the system generates proof obligations for automatic back-end provers. It's really the emphasis here is how to translate the programming language proof obligations into proof obligations for an automatic theorem prover like a CVC4 or Z3. So these are just two examples. There are other examples. If you're more into actual C programs rather than abstract algorithms, then you might want to look at C verification frameworks for Isabelle and Koch. Those exist, but none of the algorithms that we will discuss in this survey have been these frameworks, because these frameworks are really quite heavyweight because you're doing it in C, and there comes a lot of additional pain from doing things at the C level. There are other kinds of verifiers, especially dedicated to imperative programming languages. One example is the key system, where it's really dedicated to the verification of Java programs. That is its main occupation. And similarly, there's the KIF system that was initially also dedicated to the verification of imperative programs, and now it's much more general. It's really aimed at stepwise refinement, but towards imperative programs, not necessarily just Java. But these are two examples that we'll also see later on in particular verifications. And I already here mentioned the word refinement, and this is really the key, because if you're trying to verify really any algorithm, but in particular efficient algorithms with a lot of trickery in them, then if you do this straight on, you take the algorithm as is and you try to verify it, it's typically painful or impossible. So what you need is, you need to start with some abstract, typically functional version, and you refine it to an efficient imperative version. Then the pain of doing it in a theorem prover becomes much more manageable. A second problem in this refinement is that not every algorithm is deterministic. Of course, your machine, you want to refine it down. The programming language is probably deterministic, but you typically are best off to start with a non-deterministic algorithm. In particular, in graphs, you frequently have things like, for every neighbor, do something. And so it's impossible to just start from the functional programming language that you have in your theorem prover. You need something richer. And as an example of some richer framework, refinement framework, I want to talk about the work by Peter Lammich, done in Isabelle, where he has created over the stretch of 10 years now, a refinement framework with the following features. So it provides its own abstract programming language, which has non-determinism, and it has loops like this for each. But it also has general recursion, and it has specification statements, so you can start out with just specifying your code and then gradually refining it in constructs. And these specification statements, that's quite new, they also include time bounds. So you can specify and reason about the time bounds for algorithms. And then you refine things. You start from the specification level. Then you have you can do algorithmic refinement. You can refine things are not executable by things that are executable. Then you have support for semi-automatic data refinement, where you can refine things like sets into search trees. And you also have semi-automatic refinement to this imperative whole framework that I talked about, where you can, in the end, generate code in functional languages together with imperative effects like standard ML, but also Haskell or OCaml. And finally, quite new, you can also generate code for LLVM from that framework. And other frameworks are similar. This is just one example. And in fact, there's a whole zoo of provers, logics, and frameworks, and I can't possibly give you a complete overview. I just want to give you a feeling for the different choices and different approaches that you have in this area. But there are some commonalities, not just a complete zoo, but there are certain families that look alike, and in particular, many, although not all of them, all of the provers start with an internal higher order functional language or logic as the starting point. That seems to be an agreement from much of, but not all of the community. Like ACL2 and Y3 actually have first order languages. And if you want to do imperative programs, it is imperative that you have something like an ownership or separation logic. That seems to be another agreement in the field. So now, from the frameworks for this work, let's move on to some actual results. And we start with the mathematical foundation. And if you open the Cormen book, also the beginning, the first 100 or so pages are concerned with the mathematical foundations for the analysis of running times or other resources. And the key here, of course, are Landau symbols, and they are well supported in both Eberl and Koch, and both of them have an extensive analysis library. So you can reason, in principle at least, on the same level of abstraction as you do in the textbooks, although, of course, the proofs typically are more detailed. But there is more. There isn't just the Landau symbols. There is also automation. So I want to show you a little bit of the automation that we have in Eberl that makes the work, some of the work feasible. And the automation that Eberl provides starts from the so-called Acrabazi theorem, and it's a generalization of the master theorem for divide and conquer recurrences. So typically things like merge, sort, how do you compute its running time complexity? Well, it's a divide and conquer algorithm, and the master theorem tells you what the complexity is depending on certain constants. And the Acrabazi theorem is a generalized version of that. And so this is, you have a recurrence of this form, and you can, the people who know about the master theorem can already tell there's a difference to the master theorem, namely the recursive calls don't all have to be on chunks of the same size, but they can have differently sized recursive calls. And that's the main advantage of the Acrabazi theorem. And I don't want to go into the technical details here. Here you can just see some detail, some examples of different recurrence equations and their solutions. And in particular, here's one recurrence equation where you can see that the two recursive calls of the time function are on differently sized inputs. And that's something that the master theorem can handle, but the Acrabazi theorem can handle. And in fact, all of the examples above can be almost automatically. There's a tiny thing you have to do yourself in Eberl now due to some automation that Manuel Eberl, one of my co-authors, provided. And this automation is the basis for more further work, namely automated asymptotics. So this is not just Landau symbols, but limits. So Eberl can now prove automatically statements of this form that the function f of x, if x goes to some limit point L, then that function value f of x goes to some limit point L prime. Or it can prove automatically that some function is in a certain complexity class, not completely automatically for everything, but for a wide class of real valued functions or sequences involving logarithms, exponential functions, and others. And the theory is known, and similar algorithms have been programmed in Mathematica and other computer algebra systems, but they are unverified. some of the systems actually produce wrong results, and sometimes you actually get also timeouts, whereas the implementation that we have in Isabelle is actually a lot more robust than what you find in other systems. And here's an example which is actually taken from the proof of the Akrabasi theorem. In that proof, as a, oops, no, I can't do it like that, as a sub-goal in that proof, the question arises, show what is the limit of this huge expression. And if you go through it slowly, I think you will find out what the limit is. And it turns out the limit is 0, and it approaches that limit from above. So you don't have to do that by hand anymore. The system can do this automatically for you in 0.3 seconds. Actually, I think I should go into full screen mode. I just realized that would be, that's not what. Yep, that's better. Now, so much for some interesting mathematical foundations. Now let's move on to algorithms. What can we actually, what is the state of the art in verifying these textbook algorithms? And we follow the structure of CLRS, but we don't cover all of it. We focus on particular highlights. And we start with sorting and order statistics. And here I want to focus first on some imperative verifications. There is something called TimSort. That's a Java standard utility for sorting arrays. And it's a complex combination of merge sort and insertion sort on arrays, and you won't find it in any textbook. It's really been programmed by somebody called Tim. And there was the first publication in 2015 by Dijkstra and co-authors, and they had discovered a bug in the implementation, which actually a bug that was in multiple implementations of this algorithm. And they suggested some fixes, but they couldn't yet prove those fixes correct. And the bug was that with very large arrays, like at least 2 to the 16 elements, I think even more, there was an exception out of bounds was raised. Index out of bounds was raised. And then 2 years later, they had actually managed to verify their improved version and show that it terminates and that it's free of exceptions using this key system that I mentioned earlier. And I asked them whether they also intended to verify functional correctness, because they didn't do that yet. And they said, probably not. It would be a significant further amount of work. Another sorting example of sorting verifications is the C++ standard. And that C++ standard decrees that the standard sorting algorithm must have worst case execution time O of n log n. Now, not all implementations of the C++ standard adhere to that. So, for example, LLVM's libc sort has worst case execution time n squared. Why? Because it's a variation on Quicksort that doesn't completely it falls foul of the standard, some of the counterexamples that goad Quicksort into quadratic execution time. Now, Lammich and Haslbeck, they verified an LLVM implementation using this Eberl refinement framework of something called intro sort, which is again one of these highly optimized sorting algorithms based on Quicksort and more. And they proved the functional correctness, and they proved that the worst case execution time actually is n log n. And finally, by benchmarking, they showed that it has the same performance as GNU's lib intro sort. So this is another approach to verifying sorting algorithms for standard libraries. Here you don't take an existing sorting algorithm and verify that very code, but you, in a refinement fashion, you generate an implementation in here, in this case, LLVM from an abstract specification. But this shows that we are at the point where we can actually verify industrial strength code. Another example from the Cormen book is the smallest element via the median of medians algorithm. I don't want to go into the algorithm in any detail, but it's the thing which I mentioned earlier, where the Acrabazzi theorem can automatically prove the complexity. And there was an initial functional version, which you see above, by Eberl, and then it was refined later on, including the linear time proof using this Acrabazzi method. And it was refined down to imperative code by Zahn and Haslbeck. Data structures. Okay, there's a whole forest of search trees, and I will just pick out a few examples that I think are interesting. And first trees are a popular case study for interactive theorem provers because these algorithms are nicely functional. They work very well on a function level. And here, I don't want to go through this. You have a whole list of a growing list of verifications of AVL and red-black trees. That's kind of the entry level if you want to do anything in that area. And by the way, I want to explain what these references mean. So if they are underlined, they're actually links to the actual paper. If I use a conference abbreviation, then I just use a 2-digit year. So that is ESOP in 2004. This is the archive of formal proofs. If I just write a 4-digit year, then it means it's not published officially, but it's available somewhere. And this is the year when it was created. So I don't want to go into the details here, but the question is, how do you actually prove functional correctness? Shouldn't it be easy? Well, it's obvious to humans. If you look at these algorithms, yes, clearly they are functionally correct. They are simple enough. But until recently, these proofs in interactive theorem provers were more or less verbose. Why was that? I blame it on this definition of the binary search tree invariant that had to be verified. That something is a node of this form. So this is a tree with a node with a left subtree, some element, and a right subtree that is typically defined to be a binary search tree if the two subtrees are binary search trees and everything in the left subtree is less than the element in the middle, and everything in the right subtree is bigger than the element in the middle. You can do it like that, but then it typically that isn't easy to automate. And I found that what works much better is, instead of talking about this binary search tree predicate, you talk about this in blue. You say that the in-order traversal of the tree that gives you a list of its elements is a sorted list. And then automation is easier to obtain. And this works. I showed that this works really for a whole list of different more or less well-known search trees. But of course, this is only for the binary search tree invariant. It doesn't cover balance invariants. They are very specific to each search tree, and they're not automatic typically. And now I want to mention two search trees which I find quite interesting. The Cormen book. The first one are so-called weight balance trees, and they go back to the 70s. And they are defined like this. You have a parameter. This is the balance factor between 0 and 1/2, and that essentially tells you how different in size the two children of a node are allowed to be. The smaller the balance factor, the more different in size they can be. If the balance factor is 1/2, then basically half of the nodes must be in one subtree and the other half of the nodes must be in the other subtree. They can't be very different in size. So you take the number of nodes rather than the height of the subtree as the balancing measure. And insertion and deletion work as for other search trees. You use single and double rotations depending on subtle numeric conditions on the sizes of the subtree. Now, it turns out that the original papers by Niebergert and Reingold, actually the deletion algorithms, these numeric conditions for the deletion case were incorrect. And this mistake was first discovered and corrected by Blum and Mehlhorn in 1980. And then completely independently, they didn't know about the earlier paper, by Hirai and Yamamoto. And why did they verify weight balanced trees in COC? They verified them in COC because there is an implementation of a slight variant of weight balanced trees in Haskell, and somebody noticed that the implementation doesn't work properly, that it generated non-balanced trees. And so then these two people, Hirai and Yamamoto, sat down and actually verified things in Haskell and found that there is that it's much more difficult than in the original paper, and that you need to adjust things. So this is again an interesting example because it was motivated by actual code going wrong. And another one which I quite like are so-called scapegoat trees, strange name. And the central idea here is you don't rebalance the tree every time you insert an item or delete an item, but you rebuild only when the tree gets too unbalanced. I don't want to go into the details here. And that means you don't get a worst case execution time guarantee. That's nice, that's logarithmic, but you get an amortized logarithmic complexity guarantee. And so this is just to hint at the fact that the analyses that we can do in theorem provers these days are not just for worst case execution time, but amortized analysis is possible as well. And so this is a nice idea that I think is not known very much, and I just want to publicize it here. Dynamic programming. It's of course an important chapter in any algorithms textbook, and we have an approach to that based on the refinement idea, starting from a functional definition of your dynamic programming problem, and that's usually the way it's also taught these days, not by fiddling around with arrays, but you start out with some recursive algorithm. And what I'll talk about is some work by Simon Wimmer and co-authors. And the idea is you write some recursive program like the Fibonacci function, and then you crank the handle of this approach and you obtain a monadic memoized version. So you don't actually execute all the recursive calls every time, but you just execute the recursive call once, and then you memorize the result, and the next time you can go back to the memorized result and don't need to recompute things. And then the fib prime function, the memorized one, looks like this, where you have some monad with the memoization built into the monad, and what looks like a recursive call behind the scenes actually means, oh, first you look up in the table that belongs to this function. Have you already computed the, have you already come across a call of n-1? If so, just look it up in the table, then compute it. So this looks now quite innocuous, but there's a lot going on behind the scenes, and I've used this notation here to indicate this is not just a recursive function definition, there's more going on, all this memorization. And on the following slide, yeah, okay, right. So what this approach to memorization, memoized functional programming does is it gives you first a memoized definition from this one, and it proves, I don't want to go into the details of this, but it proves essentially that the memoized version fib prime is equivalent to the original version fib. And on the next, so it gives you two things for free, the translation from the standard recursive function to the memoized one, and the proof that the two are equivalent in a certain sense. And this is just the code for the memoized function, where you have the explicit lookups in the table, and updating the table. But I don't want to go through the details. So the automation is automatic definition of monadic memoized function from the original unmemoized function, and the automatic correctness proof via parametricity reasoning. That's just a technical detail. How do we realize the state or the memory of this memoized function? Well, we have two state monads that we can plug in. One is you just use a purely functional state monad based on some search tree. That's your choice. Then, of course, you have the logarithmic penalty you pay for every lookup, or you use the state monad of the imperative whole framework, and that uses arrays. And then in principle, you get the same O of running time as a standard imperative implementation of this algorithm, except that, of course, you're going through not C++, but you're going through some functional language that has an imperative sublanguage, which comes with a certain penalty in terms of constants. And as applications, we showed that we could apply this to the Bellman-Ford algorithm, minimum edit distance, optimal binary search trees, and some other examples. And you always crank the handle and you get out the optimized algorithm, and you get the correctness. And we also proved correctness of that the original recursive algorithm is correct, which is typically not very difficult. Interesting is the case of the optimal binary search tree. What is this about? This is about you have a sequence of input keys, key K1, or set of input keys K1 to Kn, and you know in advance what the access frequencies for each key will be. So you can structure your tree in an optimal way so that frequently accessed keys are near the root and less frequently further at the bottom. And there are some algorithms for building such optimal binary search trees, and there's a straightforward recursive cubic algorithm, but Knuth came up with a quadratic optimization that's not obvious. And Yao simplified the proof, and we then verified, that's quite tricky, verified Yao's proof, and we also came up also ended up at the quadratic optimized version. Advanced data structures. Of course, there are B trees. There are two verifications of B trees. One was done in the Cox system, extended with something that allowed them to treat imperative updates. And the other one is interesting. It was done in the KIF system, which is for imperative programs. And they coupled the KIF system with a three-value logic analyzer by Muli Sagif for shape analysis. And so they could discharge some of the proof obligations automatically using this program analysis tool. So that's a nice combination of interactive and automatic analysis. Priority queues are, of course, a staple of the introduction to algorithms, and there are a number of verifications of functional implementations. We have leftist heaps, we have priority queues based on Brown trees, we have amortized analysis of more complicated structures like skew heaps and pairing heaps, which are not so trivial anymore. The amortized analysis is not so trivial, the functional correctness is easy. Then we have binomial heaps and the skew binomial heaps that have been verified, and the skew binomial heaps are interesting because they're the best functional version we have. Now, all of these priority queues that have been verified, they are without a decrease key operation. In order to remedy that, Lammich also used an imperative array-based heap implementation, including the decrease key, and verified that one. And so I think we have really covered quite a lot of the standard literature on priority queues, including this tricky decrease key operation. Another very fundamental and very interesting algorithm is the union find data structure, and Charguereau, Potier, and Gounod, in a sequence of papers, managed to verify this completely, meaning they verified it in a specific framework, Chargorod's characteristic formula framework. And the approach there is that you translate the OCaml program that you want to verify into a logical formula that captures the program behavior, including the effects and including the running time. And then starting from that formula, which you import into COC, either as axiom or also recently verified, you then verify the program in COC that is starting from that axiom. You verify the properties of the program that you want to verify. And the astounding result is that they managed to verify the amortized complexity of O of alpha of n of each call. And you remember, this alpha is a very slowly growing, almost linearly growing function. If you've ever tried to teach this in class, you will know that it's not an easy proof. And so it's quite, it's really quite an achievement to have verified that in a theorem prover. Graph algorithms are another large topic in algorithms books. So how are we doing on those? Because graph algorithms are typically not so nicely functional. So let's look at strongly connected components. And the first one that was verified is the algorithm by Gabo, and it was verified by Lammich. And it was not verified just because he wanted to verify an algorithm, but this is something you may be interested in. It's used in a spin-like model checker called Kava. That is really an abstract form of spin-like model checking for LTL formulas. And it's completely verified. It's exported to standard ML with its imperative features. And it runs at, well, depending on the size of the example, 1 or 2 orders of magnitude slower than spin does. But at least it's like you have a reference implementation. And in fact, yeah, there are known defects in certain versions of spin using certain algorithms. So the best known strongly connected component algorithm is by Tarjan, and that was verified twice. And finally, the one that's actually in the Cormen book, the one by Kozaraju, was verified by Poitier quite recently. Minimum spanning trees. Everybody knows about Prim and Kuskal, except that Prim shouldn't be really called Prim, it should be called Jarnik, because that was the Czech mathematician who first discovered it in the 1930s. And this is again a popular verification topic. So we have in the literature 8 quite different verifications. One noteworthy one is the one of Kuskal, done recently by Haslbeck and co-authors, and they also proved that the worst case execution time is E log E, so where E is the size of the number of edges. Dijkstra invariably is a popular verification topic. We have 7 quite different verifications of that one in the literature for really, and I want to just point out one interesting difference here, namely the standard algorithm that is taught in class uses the decrease key on priority queues. And decrease key is notoriously a tricky operation on priority queues to verify because it's inherently has an imperative flavor. And Lammich actually verified Dijkstra twice with different implementations of decrease key. And Chargorod used a trick in an earlier publication to verify Dijkstra without decrease key. You simply leave the old the values in there and just add new smaller values, and when you get out one of the older larger values, you just discard it. Of course, it's not clear to me 100% whether this is asymptotically slower or faster than the one with decreased key. Well, it can't be faster, but whether it is really slower or not. There is one paper that claims that empirically it's actually faster to do it without the decreased key. Floyd-Warshall is also a popular topic. I don't think I want to go into the details here. Maximum network flow is not so popular. We're getting into more complicated algorithms now. And here, only recently, the Edmonds-Karp algorithm was verified, and including the running time, and also later some refined variants of push relabel algorithms. This is really not something that, not for everyone. I mean, it's quite complicated. And what is nice is that even these algorithms verified in a theorem proof were competitive with Java implementations by other people. Of course, these are not highly optimized C++ implementations. The one here by Cedric and Wayne comes from their textbook, but still it's not a complete toy. Now, here's something that I really want to mention because I think it should be in the Cormen book. The first two topics on matching in graphs. And the first one is Edmonds' famous Blossom algorithm from 1965, matching in general graphs. And I would claim this is the most complicated algorithm that I'll mention in this talk, and it was only recently verified. The other one is the Gale-Shapley stable marriage algorithm, which is the complete opposite in the sense that it's quite simple, but important enough that Shapley, it was one of the contributions that won Shapley the Nobel Prize in Economics in 2012. And I would say it's one of the most widely used algorithms in this talk. And it has been verified because it's quite simple actually 10 years ago. Finally, of course, there's a whole section on selected topics in the Cormen book, but I won't be able to cover that. I wanted to focus on randomized algorithms, but I'm running out of time, so I will quickly go through that. Randomized can be formalized in the same manner as before in pure logic, but now the idea is that you express your algorithm as a function that returns probability distribution. So you don't work on values, you work on probability distributions. And using some of that approach, as an example, Quicksort, what has and hasn't been proved is already in 2008, there was a proof that the expected running time of randomized and deterministic Quicksort, both of them have n log n expected running time, and that was later refined to give an exact value for the running time, a closed formula involving the harmonic numbers, and then using results about harmonic numbers to also conclude the n log n bound. And finally, Tazarotti and Harper recently showed some tail bounds. They showed that the probability that you hit on an input that takes longer than this n log n, that this is prohibitively small, the probability. And I could go on, but I really think I should be speeding up here. We then connected that with the analysis of random binary search trees. Random binary search trees are unbalanced binary search trees just generated from a random permutation of keys. So you just put your key one after the other into the binary search tree, and on average, it won't diverge. It won't diverge into a list. And in fact, we could prove that the expected height of such a random binary search tree is again logarithmic. So it's not as good as a black tree or an AVL tree, but it's like a factor of 2 worse if you don't do anything. And we can actually show more. We can show that the distribution of the internal path lengths is the same as the distribution of the running times of Quicksort. Treats, I think I'll have to skip in the interest of time. They are fascinating data structure, but we just don't have the time for it. And so I just want to finish with some conclusion. So first, let's compare what we have and haven't from the CLRS book. So I would say that the first 750 pages, which I would call the core of the book before the selected topics start, much of the basic material has been verified. Of course, there's always lots of remarks and further variations that we haven't verified, but the core material, I think, has been verified, except with 3 exceptions: hashing, including probabilities, Fibonacci heaps, they are in the pipeline, and the rather esoteric Van M. de Boas trees. So if you want to work on something that hasn't been worked on, then pick the first or the last item. I'm also using the results of my research in teaching. So I have a new course at TUM called Verified Functional Data Structures, where the students really learn Isabel from day one, and the first quarter of the course is just concerned with learning a proof assistant, and the rest of the course is based entirely on using that proof assistant, including the homeworks and also the exam, to introduce the students to functional data structure like these search trees, priority queues, and similar things. And there's an online book in preparation that I hope will be coming out soon. Quo vadis, what else? Where can we go from here? I would welcome if people were to tackle advanced textbooks like Randomized Algorithms by Modvani. I had initially intended to get that far, but yeah, the time is running out. And another one is interesting challenge is that you pick some challenging or poorly understood state-of-the-art algorithm, not a textbook algorithm, but something that really comes from the algorithms literature. And there are these algorithms where people say, well, yes, it's been published, but I don't really believe this, and the proofs don't hold up, etc. Of course, you need to talk to algorithms people to find out what would be a good target for such a verification. And finally, real program libraries. I would think there are some low-hanging fruit here. Why? Because there are a number of publications by these authors that also did the TIMSORT algorithm, and they verified a number of actual libraries, typically quite simple things, even linked lists. What do you find? You find overflows. It's quite amazing. So I think it's really worthwhile to apply our tools to existing libraries of industrial strength code and find that it's not completely unfailing. Okay, and that really brings me to the end of my talk. Thank you very much for staying with me for so long, and I'm happy to take questions. I don't know how this works.
Thank you very much. Thank you very much. Very interesting talk. We have time for a few questions. Please, if anyone has questions, please raise your hand and can ask questions. I have not seen anyone raise their hand. So I have a small question. You just talked about the verification, the randomized algorithm, and some examples that you show. I just find that you just verify the Las Vegas algorithm. So do you have any idea how to verify the Monte Carlo randomized algorithm?
Sorry, verify what kind of randomized algorithm?
Monte Carlo. Yeah, you have there are two kinds of randomized algorithm. One is to give the correct result, and one is to may not terminate, or one may give the wrong result in some case.
I think you can verify those. I mean, some of these algorithms have been verified, like primality tests. You can follow the methodology that I outlined, for example, to express those algorithms in a monadic fashion, and then reason about them and reason that they will, with a certain probability, give you the correct answer. So that you don't need to do anything special there.
I see. Okay. Okay. Thank you. Any other questions?
I have a question. So first,
please.
Great talk, Tobias. Thank you very much. I basically have two questions. You talked about these data structures. So, I mean, this whole, let's say, generalization of Hall logic towards separation logic also aimed at, let's say, verifying data structures such as trees, linked lists. And it's claimed that that is good because you can basically do that in a compositional way. So my first question is basically, in the kind of proofs that you provided for, or you mentioned on these data structures, is also compositionality there an important issue? So is it important to reason about, let's say, disjoint parts of the heaps?
Yes, that is certainly important. But it turns out that if you just take off-the-shelf separation logic, at least one of the students who worked on this, he worked on the Fibonacci heaps, and the Fibonacci heaps are not tree-like at all. And in the end, he just gave up and did it by brute force. He couldn't get the separation logic to work in a way that would really help him. Now, of course, that may be that the student and his supervisor, but the supervisor was quite familiar with the topic, that they did it, they weren't clever enough. But I think separation logic is not the full answer.
Yeah, I agree. I mean, also, I'm not aware of any separation logic proofs of Fibonacci heaps, by the way. I mean, this is simply a difficult thing. The second question I had is, so you mentioned functional correctness, you mentioned running time. What about termination? So termination just for non-randomized, but also I'm thinking about a randomized thing where it's all about almost sure termination, or even more complicated question like, does an algorithm have a finite expected running time?
To be honest, I'm not an expert on this, and it may well be that some of this work has been formalized, but I didn't come across it because I was focusing on the particular book, and so it's quite possible that, for example, Gilles Barthes, he and his co-workers have verified many randomized algorithms or probabilistic algorithms, and so possibly they've also gone that way, although nothing really comes to mind at the moment.
Well, thanks.
Thanks for the talk. I have a kind of a meta question. So in your experience, can you maybe describe a case that surprised you? Something like maybe when you looked at it and said, oh, this should be easy, and then it turned out to be very difficult.
Yes. In the verification of the Blossom algorithm, I actually initially worked on that as well, but then it was all done by somebody else, one of my postdocs. I spent like, I don't know, a month or so trying to find the best graph representation, the best in logic formulation of what a graph is. So in particular, an undirected graph. So should it be that your graph is a set of edges where an edge is a two-element set, or should an edge be a pair and your set of pairs should be closed under symmetry? And there were lots of these design decisions that tried various variations, and then I tried to prove what is known as Beer's lemma about undirected graphs, and I always got halfway through, and then I found the representation I had was really inconvenient, and then I started again, and in the end I never got to the proof. So I think, if anything, then I find our approach to graphs, formalizing graphs, is not perfect yet. I don't know what, I mean, undirected graphs. Directed graphs is easier. There really a relation is a good answer. But with the undirected ones, the complication you have through the symmetry, I don't think we have a good answer. And even directed graphs, reasoning about, I mean, sort of pointer chasing in directed graphs and doing that automatically. I think the theorem proving community doesn't have a good logical or automated foundation for that. But the algorithms themselves, it was not that I looked at the algorithm and thought it was easy and then it was difficult, or the other way around. It was typically, you could tell quite early on how complicated it would be.
Thank you for this insight.
Okay. Is there any other question or comment? Yeah. Okay. No?
Ah, yes, now I see something in the chat.
Yeah, okay.
Yes, right. This is the question is, what about space complexity rather than running time? Indeed, a lot less work has been done on that. In principle, this can be done, and there is work on by Jan Hoffmann and Martin Hoffmann to automate the analysis of space complexity proofs. But I think concerning the algorithms that we looked at for this textbook, I think there's almost no analysis of the space requirements. And indeed, in a functional language, it would be quite tricky to do that. So I think more could be done on space complexity. Right. I think there are no, the question is, what about concurrent data structures and algorithms? I think there are none in the Cormen book, and that's why we also excluded them. Or there's only, I think there's one small section on concurrent algorithms and data structures. And so essentially, there's of course a lot of verification on that, but none or almost none that intersects with the Cormen book. And that's why I didn't consider it here.
Okay, sure. Okay, any other questions or comments? Otherwise, let's just turn to the very interesting talk by Tobias. And also, thank you very much for your very great job to verify so many algorithms so that we can use the reliable algorithm in our lab later. Thank you very much.
Thank you for the invitation. It was a pleasure to speak. Bye-bye.
Bye-bye. Bye-bye. Now it's a coffee break for half an hour, and the next session starts from 10:30. Thank you.